Welcome back to the Save It for Parts channel. Today we're starting a project that I've been putting off for quite a while, mostly because I have very little idea of how to do this. I know what I want, but I'm not quite sure how to achieve it. If you follow my channel, you know I'm into satellite tracking, weather satellite downloads, and general space-based experiments. One thing that I really lack, and which would really help me in my satellite experiments, is a large tracking antenna. I have this folding antenna, or C-band satellite dish, and that works pretty well for geostationary satellites. As a quick refresher, those are the ones that sit over a fixed point in the Earth, at least from our perspective, and they do that by orbiting at the same speed that the Earth rotates. Now, a geostationary satellite is about 22,200 miles above the Earth's surface, which for a 12-inch globe like this would be approximately 3 feet away. So to scale, our satellite would be way over here. So our satellite is orbiting at 22,200 miles. The speed at that altitude equals the rotational speed of the Earth. So that's why geostationary satellites always look like they're in the same spot to us on the ground. And that's why most satellite dishes, like the one I have out here for the GOES East satellite, stays fixed in the same location. The satellite is always in the same place to us on the ground, so the dish is always aimed in the same location. Once you have it dialed in, you have it tuned in, you have your strongest signal, you just leave the dish pointed that way forever, and it always gets a good signal. The other thing about a typical fixed satellite dish is that if it does move, say to track different satellites in slightly different orbits, it only has to move from horizon to horizon, and it only has to move in a certain arc, basically above the equator. I'll throw some overlays up here to see what that actually looks like from the ground. This was using a little microwave imager that I built out of another satellite dish to basically see geostationary satellites using their radio emissions. So from our perspective on the ground, they are in an arc known as the Clark Belt, and if you have a motorized big C-band satellite dish, it only has to follow that arc. It doesn't have to move to any positions outside of that. So it'll use something called a polar mount and a one-axis linear actuator or motor. So it basically only moves in one curved track. Now that's all great for geostationary satellites, but my problem is I want to look at low Earth orbit satellites. There are a bunch of interesting things in low Earth orbit that's somewhere much closer to the Earth, like 300 miles in altitude. Starlink satellites are up there, the International Space Station is in low Earth orbit, the Hubble Space Telescope is there. There's all kinds of weather satellites, scientific satellites, government satellites, military satellites. At this altitude, an orbital velocity is much faster than the Earth rotates, so these satellites go around about every 90 minutes to us on the ground. Anyway, what that means in practical terms is that to track a low Earth orbit satellite, to keep an antenna aimed at it for maximum signal, you have to be able to move that antenna fairly quickly. The satellite goes from horizon to horizon in approximately 15 minutes for a really good directly overhead pass. And they're not always directly overhead. Sometimes they're off to the side, and you only get 8 or 10 minutes of good coverage. So your dish has to be very flexible. It has to be able to move in essentially 360 degrees around in azimuth and 180 degrees in elevation, or up and down. And that gives you the maximum coverage, the maximum time for signal reception from a passing low Earth orbit satellite. Now, I've built something like that before. This is an old security camera pan tilt mount. It can move essentially 360 degrees around, 180 degrees from horizon to horizon. It's controlled by an Arduino microcontroller that then plugs into a computer, and that tells it about the satellite's orbit. It tells it where to point, and then we can read out the signal coming in through an antenna and a software-defined radio along with some filters and other equipment. Now this one works great for certain frequencies. This is actually an old wireless networking dish. It's about 30 inches in diameter or so, and that's on the small end for a satellite dish. That works for pretty strong signals. It works for higher frequency microwave signals. The bigger the dish, the wider the range of signals it can take in and the more signals it takes in. So a really big reflector will collect more of the radio waves coming in and focus it onto the actual antenna hardware in the center. And then the dish itself doesn't really care what frequency is coming in, but if it's less than the wavelength of the radio wave coming in, it's not as efficient. We basically don't need to know any of those technical details. All you really need to know is that a bigger dish is generally better. Now there's a whole alphabet soup of microwave radio bands. There is C-band, which you might be familiar with from the old style 1980s satellite television. That was something like 3.4 gigahertz. There's S-band, which is around 2.2 to 2.4 gigahertz, or similar to modern Wi-Fi. There's Ku-band, which is another one you might be familiar with. That's up around 12 gigahertz, and that's what the smaller satellite dishes use that you see on houses today. There's also Ka-band, which is similar to Ku, but is more used for data, satellite internet, things like that. And then there's stuff like X-band, which is getting pretty high up there in the frequency range and requires a little more equipment, more expensive equipment, stuff that I don't have at the moment. What I'd like to look at with the bigger dish here is stuff like S-band, that 2.2 gigahertz, maybe some C-band. There isn't too much that still uses that. I think the Russians use that for some weather satellites and whatnot, but I want to be able to pick up some of those signals, and they tend to be a little fainter than Ku-band, a little fainter than the low Earth orbit L-band. So we need the bigger dish, and I'd like to be able to track that dish. I'd like to be able to move it to follow those low Earth orbit satellites as they pass overhead. Now, you've seen in other videos, I've done that by hand with this dish. I've sat on the ground, I've held the entire dish up in the air, and I've waved it around like an idiot, and that kind of works, but it's not very effective. I am not very consistent as a dish rotor. I wiggle, I fidget, I get bored sitting there for 10 minutes trying to hold the thing up. My arms kind of don't like to be in one position for very long, so I don't always get a consistent recording of the data coming from the satellite because I'm not aimed at it very consistently. Gosh, I talk a lot in these intros. Let's jump right ahead to building something. So we've got some old antenna rotors here. These are little motors that would rotate a TV antenna, and we've got the control unit for those. My friend JT found some of those at a thrift store, so thank you, those are awesome. I have another bucket with some more rotors and then a linear actuator, so this is kind of just a piston, and this might work a little better for the vertical motion. I also have some of these satellite positioners and locators that I found at Axeman Surplus. These are designed more for those linear actuators on a polar mount, so they're just basically moving it east-west. They're just a single axis, single degree of freedom. Maybe not too useful for this project, but we might come back to these at some point. Now, these things are all pretty old. Nobody really uses antenna rotors anymore. Nobody watches analog TV anymore, and you don't really need to rotate a TV antenna. Some of these have been up on towers since, I don't know, probably like the 1950s based on the look of some of them. The wires are broken, they're rusty, they smell mildewy. I don't know how many of these work, so might have to do a little experimentation to see what combination of rotors and controllers will function. Well, this one only has 3 wire controls where the other ones have 4, but this one does come with a manual, so might be able to adapt this to some kind of modern computer control. Let's see how bad things look on the inside here, and if we need to lubricate it or anything like that. It's got one of these stupid circlip things holding the drive shaft in place. I hate those. I've got a tool for that somewhere, but I never use it because there's only like 3 things in the world that use that, and it's very annoying. It's time for another cat break. There is literally a stray cat meowing at the garage door right now. Oh, it's you, Oliver. Hello. This is one of the neighborhood cats. Hi. Oliver, you want a treat? You're not really into treats, are you? Oliver's less friendly. He wants to come around and he wants to be in the garage, but he doesn't actually want that much human attention. I have to keep the door closed lately because the stray cats and the neighborhood cats just come in and out of the garage. I really need to just put a one-way cat door down there so I don't trap anyone in the garage. All right, cat break is over. I found the stupid circlip tool. I'm probably not supposed to do this. It's probably supposed to be maintenance free, but if this thing is really from the 60s or even the 80s, it's going to need some maintenance before we use it. We've pulled that out and many ball bearings have escaped. Boy, look at the weld on that sucker. I don't know if that's original, how it was designed, or if somebody came in later and bashed that back together. It doesn't look very professional, but I guess the consumer would never see it under normal operations. It probably was a good idea to open this up because all the grease is kind of dried and caked on here, and it was really stuck. So I kind of forced it apart. It doesn't actually seem to come apart more than this. I think originally we were supposed to be able to pull this pin out, pull this gear off, but Billy Bob went kind of nutso with the welder there, so this is pretty much permanently attached. I'll try and scrape out as much of the fossilized 1960s grease as I can, and then we'll put some new axle grease in there and maybe some silicone spray on the motor. Well, now that we've spent half the day taking this apart and greasing it up, let's see if it actually runs. So this one works. On the downside, it is 30 volts AC to the little motor here, so that's kind of a weird voltage. It's going to be difficult to find a 30 volt power supply unless I just hack this thing apart, and then yeah, we're going to have to run that through some relays and other garbage to get a microcontroller to run it, but maybe we've got something that'll rotate the dish. My actuator here is 24 volts DC, so I'll need yet another power supply just to run this thing. I think this one's going to be a little bit overkill. This is a big, beefy actuator that moves pretty slowly and has a limited range of motion, so I don't know if I actually want to use this one. This one will push up to 200 pounds. I do have this other linear actuator from Axeman. This one has a longer stroke, so a little bit more flexibility in how far it will travel. And unfortunately it is also 24 volt DC, so either way I think we're gonna have to get a 24 volt power supply. Now I've seen people use two of these things for a 2-axis rotor, one on top of the other, and that works fine for lightweight antennas like a 2 meter, 70 centimeter hamsat antenna. I don't think that's going to be quite enough for our dish. The weight of the dish is not that much, but the torque is all wrong. All the weight is kind of way out off center. So it gets kind of complicated trying to get motors that will handle that amount of torque while moving smoothly. We could put some counterweights on, but that just adds weight to the whole thing. This would be a lot easier if I had a welder set up. I own one, I just don't know what kind of power it needs. I don't have a welding helmet, and I just haven't had time to dig it out and learn how to use it. So I'm reduced to just piecing together scrap metal that I've got and seeing what things fit in other things. So I don't have any of the motors hooked up. I just wanted to do kind of a sanity check and see, does everything clear? Is everything stable? Is it going to hold together? And how easy will it actually be to move this thing around? I'm noticing a few issues right away. It's much harder to unfold the dish when it's kind of up over my head like that. For an initial test, I've got a satellite coming over here in a few minutes. I'm gonna try hand tracking it on this mount. And again, just to make sure everything's working right, to make sure I'm not missing anything obvious, make sure everything moves fairly smoothly, clears everything. So I went ahead and added a counterweight, basically just duct taped a giant piece of steel onto a metal rod coming out of the back of the dish. So I'm not sure if you can see it all in the sun glare here, but we have an L-band helical antenna. This is based on a 3D print from Derek SGC. He's another great satellite YouTuber. People should go subscribe to him as well because he has some great content and he releases cool 3D prints like this that you can use to make antennas. Now hooked up to the back of that, we have our Nuelec Sawbird GOES filter in LNA. So that's a low noise amplifier and filter. So basically filters the spectrum coming into the antenna down to just around 1.6, 1.7 gigahertz and then amplifies that range, so we're getting a better signal down to the software-defined radio. I'll put links to all that stuff in the video description. For the radio receiver into this project, I'm going to be using my Nuelec HackRF1. So this is kind of a higher-end software-defined radio, or SDR. And I've just recently received this from Nuelec, and I've been looking for excuses to try it out, so we're going to give that a shot, hook it up to our laptop, hook it up to the antenna out there, and see what we can receive. This is a little bit more expensive than the SDRs I've used in the past, but so far I think it's worth it. The frequency goes up a lot higher, it's got a wider bandwidth, and it's got a lot more features. Okay, we should finally be ready to go with this thing, but I've screwed around with it so long setting it up that we've missed the pass I wanted to do. We had one of the Russian Meteor satellites coming over. I was going to track that, get the L-band download from it, but that was half an hour ago, so this took way longer to set up than I thought. But it's good to know, kind of growing pains, figuring out what works here, what doesn't work, and I still don't 100% like this setup, so things are probably going to change along the way of this video. So one kind of obvious problem is that the pivot here is off. The center of gravity, center of balance is up here, and the actual pivot is down here. So when this pivots around, again, it's putting torque in the wrong places. The center of mass should be right on the pivot. I don't actually know how to do that with what I've got. I'm just building this out of junk, as I do with all my projects, so I'm using what I had on hand. This thing here, I don't actually know what this is, but it was $5 at University Surplus, so I couldn't pass up $5, and it looked like a pivot, so we slapped that in there. We might change this around. Again, I have to think about it a little more and figure out how can I do this better. As I mentioned earlier in this video, and as I've mentioned in other videos, I don't really know how to do this big motorized dish mount. This is why it's been taking me so long to do this. I've been talking about this literally for years and trying to think of how to work through it, and I still don't know what I'm doing. Now, I have some of these smaller azimuth elevation rotors. This is technically another security camera pan tilt mount, but again, these are not strong enough to handle a dish that big, to handle the torque from something off center. This is another similar unit I've used in the past, so I've played around with commercial products like this, but they're not designed for what I'm doing with them. So I would love to find a really, really big pan tilt unit that can handle a big heavy dish, but so far I have really struck out on finding a commercially available unit that's strong enough, heavy enough duty to do what I want, and it's affordable. Like, yeah, I could pay a couple $1,000s for a big one, but I don't want to pay a couple $1,000s. This is the Save It for Parts channel. I want to use repurposed surplus junk if I can help it. Not only to keep things out of the waste stream, but also I don't have a lot of spare money kicking around. So I want to find the cheapest possible solution that still actually works. So far with this project, I think we have the cheap aspect nailed down, but I don't know yet about the stable, reliable, or effective aspects. All right, well, as usual with the first try of any of my projects, absolutely nothing worked with that. I couldn't see the signal at all. I had issues tracking the satellite, and we didn't get any recordings. So this is a very frustrating hobby. It's fun, but it's a very frustrating hobby that never works right on the first 6 or 8 tries. I am still struggling to find a heads-up display that will tell me on the phone where's the satellite. Now, I hunted around a little bit and I couldn't even find the signal. I had my gain all the way up, I had the bias T on, I had the filter on, got nothing. So maybe there's something wrong with my feed line, maybe there's something wrong with my antenna, I don't know. There's a lot of trial and error that goes into this stuff, and I'd like to move myself towards a permanent installation versus stuff that I pull out of the garage every time there's a satellite pass and I have to piece together from spare parts. I would like to have something that is just set up all the time, has all the best stuff, all the connections double checked, all the antennas known working, and I can debug one piece at a time versus trying to debug like 8 different potential failure points every time I do this. So that's again why I'm trying to do a motorized system. I might actually change around the pivot point here. I've taken this off. I want to lower this part so it's closer to here, so it's closer to the actual pivot. All right, that's still not perfect, but we've got it a little bit closer to the pivot point now. I wasn't completely happy with any of the linear actuator options that I already had, so I went down to Axeman Surplus and picked up another one. Hopefully we can get this hacked in here and have it move our elevation up and down. I'm not very happy with this. There's a number of problems cropping up, not only the problems that we already had. The actuator arm, I think, is going to interfere with the dish. Also, the mounting point down here, this is not strong enough. This is just gonna bend. Yeah, I can't think of a better way to do it at the moment. Yeah, ideally, the actuator should be right up against the column, pushing on the bottom of this. Yeah, again, this is all very seat of the pants engineering. I don't actually know what I'm doing with this, as I said before. And again, this is why it's been taking me so long to get around to this, because I have only the slightest idea of how I want to do this and how to implement a 2-axis motion control system that's both strong enough, smooth enough, accurate enough, all of those things for a satellite dish. Now, I have a couple other confining factors that are contributing to my design decisions here. I'm trying not to permanently alter anything important. So since I don't know if I want this, and in fact, I'm pretty sure that I don't want this setup, I'm pretty sure this is not going to work, I'm trying not to change anything that I'll regret later. So I've made it so I don't have to change anything on the satellite dish. It will just slot in here as is, the same as it slots into its own preferred mounting hardware. I also have not changed anything on the linear actuator. It is just held on here with the 2 mounting ports that it comes with. I have not shaved anything down. I have not drilled into it. Boy, I am really chatty in this video. You can tell I have no idea what I'm doing because I'm doing more talking than building. All right, time to give this terrible thing a try and see if it's going to work at all or just collapse under its own weight. So all those problems that I thought were going to happen are starting to crop up. The linear actuator is actually too fast. The way I have it balanced here just whips that dish up and down. So I think that's going to be a little too much for fine detail tracking. The rotor works at about the right speed, but I can really hear it struggling, and I think that's because it's not balanced correctly. So there's a lot of kind of angular torque on the rotor, and it wants all the weight to be centered in the middle, and as the dish moves around, that weight distribution is still changing. It's also just not stable enough in general. I don't know if you can see, there's a light breeze, and the top of the dish, yeah, everything wobbles, so it is not a stable observing platform. Now, the one thing that actually worked well, when the dish is fully dropped into the horizontal position here, the excess linear actuator actually does clear the mechanism here, just barely sneaks by. So that's another reason to have it positioned out this far, is that it actually slides right past the dish itself. I still think it shouldn't be out this far because it is putting a lot of pressure on this bolt, and this bolt is too long. So this isn't bending yet, but it's definitely not going to last long term. So a little bit of plus, a little bit of minus on that design choice. All right, I think I may have now killed the rotor. Trying to rotate the dish in this fully down position, the rotor has given up. These are the wires from the actuator, so those don't need to be hooked up. But yeah, this thing is not doing anything anymore. Actually, this part is now a little broken because this inner dial with the red dot should be staying put, but it's getting caught now and moving with the outer dial. So that part's broken. This part is broken. This thing works great, but it's actually too fast. Yeah, the whole assembly here is really too weak, too fragile. Counterweight is not ideal. The base is okay. The base has been putting up with all the dish movements without even any extra weight on it, so that's perfectly fine. Okay, I got the rotor working again, at least for now. Let's try, before we just completely give up on this, let's try to aim it at a satellite. We're not going to try tracking a low Earth orbit satellite. I think the motion is just too jerky. It's not going to be accurate enough, but we could try a geostationary satellite. So let's try aiming it at GOES East, the Geostationary Operating Environment Science Weather Satellite. This is the wrong feed for it. This is a helical feed. GOES uses a linear feed, but everything's basically wrong, but we might be able to get a little bit of signal, so let's try that. And heck, I could always use an excuse to bring out the Cyberdeck. All right, so these are theoretically both aimed at the same satellite now. The big dish up top is permanently aimed at GOES East, and I've got my little mobile dish here, theoretically aimed in the same spot, but unfortunately it is just not quite accurate enough. I am not getting any kind of signal, and with the GOES satellite you have to be aimed pretty precisely, and this just does not have the precision. Unfortunately, this is about as precise as I can move this rotor. So you see it bounces all over the place, it jerks, it jumps. It is really hard to get a precise degree aim point with this. Heck, it's not even accurate enough to lock onto a geostationary satellite, which should be pretty easy. So unfortunately, this particular motion control system, rotor system for the dish, is no good, and I've been suspecting that since I started. It's janky, it's inaccurate. As I said in the Discord channel, it is made out of scrap metal and compromises, which somebody immediately said I should put on a t-shirt. Maybe I'll do that, maybe not. Unfortunately, it's not very good for antenna rotation, so I'm gonna have to think a lot harder. We're gonna have to go back to the drawing board, figure out how to eliminate a lot of those compromises, how to make this work better. And unfortunately, I still don't know how to do that. I've got some ideas, but I don't have a really solid path forward. So I'm going to have to spend more time considering looking at the equipment I have. listening to the goose scream at me in the background. Yeah, I think we might have to wrap this video up. Unfortunately, it has not been much of a success. We've gotten some dish motion, we've gotten some nonsense put together, but we really haven't gotten much out of it. So I hate wrapping up the video here, but I don't really have time to work on this right away, and I don't know what to do with it next. And I also hate to just shelve a bunch of video and keep it floating around my hard drive forever. So I might as well wrap it up, call this part 1. We'll try to make a part 2, maybe a part 3. It just depends how long it takes to get this working the way I want it. If anyone has any suggestions, please put them in the comments. I do get a suggestion frequently of, why don't I just use a telescope mount? Well, again, that would be thousands of dollars for a telescope mount that could hold this much weight, and they are usually a polar setup, so not quite ideal for tracking low Earth orbit satellites. It'll work, but it adds extra steps, and it's just as expensive, if not more expensive, than getting a real satellite dish rotor. So yeah, if I could find a big beefy telescope mount in the trash somewhere, or for just a few $100s, I would consider that. But I'm also looking for security camera pan tilt mounts in the trash, or for a few $100s. I'm also looking at actual ham radio, amateur satellite, moon bounce, rotor systems in the trash, or for a few $100s. Very rare that that sort of thing shows up, but I'll keep an eye out at garage sales and estate sales and auctions and whatnot. Anyway, I have done far too much talking in this video. I am going to shut up now. We're going to end this. Thank you to everyone for watching if you did stick through the whole thing, and we'll see you next time.